So picking up where we left off in the previous video, we were looking at ranking the best to worst nucleophile, and we were playing around with the solvents in this example to figure out what would go on as far as nucleophile strength. And then we come to part B. And part B, we have two really to choose from in a normal aprotic solvent type of environment. So this is traditionally which one's the prettiest, which one's the ugliest. Okay, so we got two choices here. One is an oxygen with a negative on it on a benzene ring, and one is an oxygen with a negative on it on a cyclohexane ring. So I go to my list and I try to find my first one. So this is an oxygen with a benzene ring. And if I look, well, here's a benzene ring, but that has a SO3 minus on it. And I don't really see any other group that has a benzene ring other than that one, and that's not what I want. My oxygen is attached to a benzene, not sulfur, not this SO3 group. So my benzene ring with the O group is nowhere to be found on here. Not only that, but if I take a look at my other choice that I had, the O on the cyclohexane ring, well, I don't really see O on a ring system at all. I see O on an alkyl group, so maybe it's something similar to that, but I don't really see a good match because of that ring structure. So this chart is actually not going to help us at all. So we're going to have to pull out maybe some other stops to answer this question, some other tricks that we've learned along the course of the way to figure out really which is the best answer here. Well, that requires us to go back and talk about the definition of a nucleophile. And we said a nucleophile is something traditionally that's negative. And what we've seen before in the past is something like NH3. And NH3 gives us this NH2 minus if we take away a hydrogen, right? So if we take away a hydrogen, that is really by definition an acid. And acids and bases are really the underlying message when it comes to nucleophile and nucleophile strength. That is why if you look on this chart and we go up to the top, you see that this middle column is actually pKa's. And if you look at the pKa's, we went through this whole description talking about iodine, bromine, and chlorine and fluorine. We looked at their pKa's for the acids, and then we ranked them accordingly. So we saw that very strong acids were very weak bases. They were very good leaving groups. So the same thing has to be done here. We've got to take a look at maybe acid strength. Which one of these would prefer to be in an acid form over the other? Okay, so that requires us to draw the acid forms of each one of these. So we get a benzene with an O minus, but I want to draw the acid form. So I'll take that minus off, and then I'll put hydrogen here. And then we have this cyclohexane ring, and that was an O minus. So what I would do is that I would erase that negative, and I would put a hydrogen there. That's what they've done in the chart, so that's what I'll do here. So now I've got this benzene with an OH and cyclohexane with an OH. And I need a question, which one of these would be the better acid? And that will help me determine which one would be the better nucleophile. Okay, so which one of these would be more willing to give up the hydrogen? That's what we're asking here. Which out of the two would be more willing to donate a hydrogen in solution, because that by definition is an acid. It is a proton donor. Well, this could give up a proton, and it could end up with an O minus. This can give up a proton, and it could end up with an O minus. Out of the two, the benzene ring would do it a little better. And you need to really look at why. And the reason is because if this hydrogen leaves and we get a negative that forms on that oxygen, This negative charge can participate in delocalization in the ring, and the molecule loves when delocalization can happen. So out of these two, I don't need a pKa chart. I don't need an appendix to look up the pKa values. Out of these two choices, this would be a better acid. And the reason that this is a better acid is because once it gives up the H, then delocalization can help stabilize that molecule. And that is really persuasion enough for the molecule to dump the hydrogen by the curb and then go on about its business and start delocalizing with itself. So that is the better acid. So out of the two, this is the better acid, therefore that is classified as the stronger acid. Now let's look at the chart and see how this is ordered. If I look, my pKa for HI is negative 10. My pKa for HBr is negative 9. My pKa for HCl is negative 7. And this chart basically ranks things based on acid strength. So my strongest acids are up at the top of the list. And my strongest acids are my better leaving groups. They are the weakest nucleophiles. That is the relationship that you need to take away from here. So nucleophiles, strong acids are good leaving groups. And good leaving groups are very weak nucleophiles. They don't want to be attached, right? They got rid of that hydrogen for a reason, and that is to become negative. For whatever reason that was, they are becoming negative. So that's why they got rid of that acid. Well, they don't want to become neutral again as much as something else. So because this is the stronger acid, this is the weakest nucleophile. Therefore, in DMSO, out of these two choices, this would be our better nucleophile, number one, right here, and this would be our next in line. This would be our weakest nucleophile out of the bunch. Again, it's all due to stability. This molecule's stable the way that it is, so it doesn't desperately need to find another bond to hook up to, versus something like this where delocalization is not helping stabilize that molecule at all. And then finally, the very last example problem is here. This is starting with an alkene, and I want to know what would I add to that in order to get something that looks like this molecule here. So I've got 1, 2, 3, 1, 2, 3 carbons. It looks like I probably need to add on that piece onto the organic in some form or fashion. Before I can do that, though, I've got to have some kind of halogen to substitute, right? In the alkene reactions, we never talked about how can we put a ketone group onto an alkene. But we did talk about how we could take something like an alkene and add HBr to it and brominate it. So CH3CH double gets broken down to a single. Two sites of attachment open up. Hydrogen plays with other hydrogens, so that would go here, and then my bromo would go in the other spot. The problem, though, is that this halogen is in the wrong position. If I look at this functional group, this is at the end of the molecule. And right now, this is not at the end of the molecule. This bromine's in the middle. So this is not going to work for me. I need to figure out somehow to get the bromo on the end of a molecule. And there was a trick during that time, and you've heard me mention it before, and I'll keep mentioning it, is that if you want to reverse the roles and you want an anti-Makhovnikov reaction to happen, the easiest thing to do is introduce peroxide. Peroxide H2O2 will flip the reversal almost every single time on you. So that way, what you would see happen is that the H would go on, but it would go here, and the bromo would go on, and it would go there. It's an anti-Makhovnikov reaction just by simply adding peroxide to the mix. Okay, but this is not what we need as a product, so I need to add on a substitution reaction here. Bromine needs to come off, and what we want to end up with is a C double bond O with a CH3. So that is what we would add as a nucleophile to kick the bromo off, and this group goes on in its place. So, a little bit of mixture of delocalization, a little bit of mixture of acid and base chemistry, a little bit of mixture of reactions of alkenes, maybe reactions of alkynes could show up on the test, and now substitution reactions get dumped into the fold as well. So again, it's a building up process. You've got to go back and brush up on some of those things if you're really uncomfortable with it.